In a comment, someone asked me how you could take the information shown here and find the area of the sector bounded by segment OP, segment OB, and arc PB. In other words, this sector right here. It turns out to be a pretty complicated problem, but I'm going to break it down for you in this video. This is going to be a three-step problem, and the first step is to find the radius. So notice that this is the radius, but this is also the radius. That's kind of the key, recognizing that both of these will be the radius. I'm going to label this radius R. Now look at this little segment right here from O to M. The entire yellow segment, of course, is the radius, but I see this part up here at the top is 3. That means that from O to M, this is going to be the radius minus 3, right? It's the whole radius minus the extra part that is 3. So that enables me to set up the Pythagorean theorem on the triangle down here. So we're talking about leg squared plus leg squared equals hypotenuse squared. So that means r minus 3 squared plus 5 squared is equal to r squared. Just doing leg squared plus leg squared equals hypotenuse squared. If I do r minus 3 squared, that's r minus 3 times r minus 3. Okay, and 5 squared is 25. If I multiply this out, doing a double distributive property, this is going to wind up being r squared minus 6r plus 9 plus 25 is equal to r squared. And this is going to be r squared minus 6r. I'm combining these like terms right here. That's 34 is equal to r squared. Now I'm noticing that we have r squared on both sides. If I were to subtract r squared from both sides, then both of these are going to cancel out. Be careful, on the right hand side there's nothing left, but I need to put a 0 over there as a placeholder. So I've got negative 6r plus 34 is equal to 0. I'm going to go ahead and add 6r to both sides. So that's going to give me 34 is equal to 6r. If I divide both sides by 6, I will have the radius. So the radius is equal to 34 divided by 6, which reduces down to 17 over 3. So that's the end of step 1. We now have the radius to use in step 2. Step 2 is to find the measure of angle O, which is right here. Now, we're going to wind up using either sine, cosine, or tangent. I don't know if your teacher has ever said SOHCAHTOA to you. SOHCAHTOA. It's just sort of a one-word acronym representing the 3 definitions of the trig functions sine, cosine, and tangent. This reminds us that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So of course the radius here across from the 90 degrees, this is the hypotenuse. We're looking for the measure of angle O. So if I look across from angle O, that's going to be the opposite leg. And the green side right here would be the adjacent leg. Now I have numbers for the hypotenuse and I have numbers for the opposite leg. I have nothing for the adjacent, so that's not actually going to help me out at all. So I'm just going to focus on the fact that I have opposite and hypotenuse. And when I look over my SOHCAHTOA, I realize that's going to be the sine function. Sine is opposite over hypotenuse, and those are the numbers that I have. So I'm going to set this up by saying the sine of angle O. All right, that's not 0, I'm using letter O. So the sine of O is opposite over hypotenuse. So that's going to be 5 over 17/3. Now remember, when you divide by a fraction, you have to multiply by the reciprocal. So this will be the same thing as 5 times 3 over 17. You multiply by the reciprocal. Now this is 5 over 1. So if I multiply this together, I have that the sine of O is 15 over 17. So when you're looking for the angle, you need to do the inverse trig function. So if I want to find the measure of angle O, I'm going to do the inverse sine, a little -1 on it, the inverse sine of 15 over 17, and that's going to equal the measure of angle O. So I can just put this in my calculator. All right, so I'm going to do inverse sine, so second sine of 15 over 17. All right, I'm going to keep 3 decimal places for now because I'm going to have to use this to find other things, and I don't want to have too much error. So I've got 61.928. And that is the measure of angle O. And that's step 2. We have 1 step left. So step 3 is to find the actual sector area that we were asked to find from the start. Keep in mind that we already know the radius and we already know the central angle from the previous 2 steps. So how do we find a sector area? Now, I'm about to write down a formula for sector area, but I want you to understand where each part of this formula is coming from. So what I always think when I think about sector area is always going to be some fraction of the total area, because the sector area is like one slice of the whole pie. So here's the formula. The sector area is always going to be some fraction. Now the fraction is going to be that central angle divided by 360, right? So theta over 360. And then the total area, well, what's the formula for the whole area of the circle? It's pi r squared. So look, this is the formula for sector area, but hopefully you understand a little bit better where this is coming from. It'll make it easier to remember. We know theta and we know r. We found them from the previous step, so we can go ahead and just substitute those in and find the sector area. So it's going to be the 61. All right, so the area is going to be the 61.928 over 360 times pi r squared, and the r is the 17 over 3. So I'm going to have 17 over 3 squared. And this is it. I'm just going to put this entire thing into my calculator, and that will give me the sector area. Here we go. So I've got my 61.928 over 360. And then I've got pi times 17 over 3 squared. And there you go, 17, and I think I'll round this down a little bit more now. I'll round it down to 2 decimal places, so 17.35. And whatever the units would be square units. So I'll just say units squared. And that would be the area of the sector.